vector equation of a line is another great application of vectors. We're going to be able to do the same idea as y equals mx plus b, but using vectors. And this is going to be really helpful because your normal y equals mx plus b only worked in 2 dimensions. But what happens if something's traveling in a straight line in 3 dimensions? How would you go about doing that? And then you could obviously, once you started with that, you could go if something travels in a parabola in 3 dimensions. But we just stick to the vector equation of a line of something in a straight line. So what we have here and what we've done already, we imagine 3 points in a straight line. We've got point A, we got point R, and we got point C traveling in a straight line in 3 dimensions. We can set somewhere up to be the origin in our 3-dimensional space, and then we would have position vectors A, R, and C. And the basic idea of the 3-dimensional equation of a line is that you can get to any point on this line as long as you have a starting point on the line. So let's say I'm starting at A. If you had another point on the line, and this is true for y equals mx plus b, if you want an equation of any line in 2 dimensions, you need 2 points. So you want an equation of a line in 3 dimensions, you need 2 vectors. If you have the vector A and the vector R, the vector A and the vector R can get you the vector AR. We can do that by going minus A plus R. So A to R would be minus A plus R, and we will call that our direction vector. So once you're at point A, somewhere in 3-dimensional space, and you have a direction, someone just tells you, well, you want to find somewhere on that line, go in that direction a certain distance, right? If we look and say, oh, this looks like from A to C, looks like 2.5 times A to R, you just tell your direction vector, hey, go 2.5 times from A to R, and you'll get to C. If you want to get to another point on the line, you just have to go up this distance from A to R, go more of that. So we have our, I'll add these arrows on here. We have our equation of our line. Oh, and this time I used A to C. We're going to label these. So R is any vector on the line. And what's nicer with vectors compared to y equals mx plus b, y equals mx plus b has only one point you're starting with. That's b is your y-intercept. And then m is your slope. Okay? All of this c minus a is like our slope, but in vectors we just tell it as a direction. But the direction you're going is like the slope that you're going. Because when we had slope with a line, this rise over run tells you go over 2, up 3, gets you a certain point. Now we're just saying that's your direction that you're going. You can start with any vector, and then you have a direction vector, and then t is just a constant, a parameter, telling you how much to go in that direction vector. It can be positive, it can be negative, it can be decimals. top of these ones. And so the vector equation of a line is very much like y equals mx plus b, except instead of slope, you have a direction vector. Instead of b as a y-intercept, you can start with any place. And we can even do stuff in 2 dimensions or 3 dimensions. So we could redo all the math that you learned in grade 10 with vectors, but it's going to be more helpful for us to do lots of math in 3 dimensions. So you've got a point, x comma y, and you've got 2 vectors, a and b. Then this equation, which is the vector form of the equation, right? Any point, direction vector, and then this finds any other point on your line. You can just look at the corresponding coordinates. And if you multiply t into here, then color code this, the x coordinates would make that equation. Color code the other one, the y coordinates would make this equation. This is called the parametric form. And we have these different forms which we switch in between because each form helps us with something. So if we're looking at specifics for x and y, the parametric form is really nice. If you solve for the t, in other words, in the parametric form, it would not be hard to manipulate it to get t by itself. If you solve for the t in both of those equations, then you could use substitution to make both of those equations the same, and this would give you the Cartesian form. Cartesian form is what you did in grade 10. Everything that you do on a graph paper, sometimes a graph paper is called a Cartesian grid, named after René Descartes, a French mathematician, who was the first one to think about putting things on a graph. Like, oh, I think he was watching a fly. And it was like, oh, if we just say it's this far away from the window or something like that. I'm probably totally wrong. I'm making this all up. But something simple. I wish there was fancy math you could do now. It's like, oh, I looked at a fly and now I'm famous. Right? An apple fell on my head and now I'm famous. I don't know. I have to do something extremely simplistic and stupid at the same time, and maybe I will become famous. Hundreds of years from now, kids will be learning, oh, this is JR math. There we go. So let's look at something that you have done already, 2 dimensions. Let's look at it in vectors and see how nice it is. Okay? So in this case, we have a random vector A, and I'm going to write it like this. If we imagine A, here's our origin. Here's the point 2, 5. This would be the vector of 2, 5. That point is on the line, and it's parallel to the vector 3, -4. That tells us our direction. Our direction vector will be 3, -4. That means if I want to find another point on my graph, I could go over 3, 1, 2, 3, and up 4. Or down 4, not up 4. -4, so that would be at 5, 1. There's our line. The purple one is our line. We know that 2, 5 is on that line. And we know that if we went over 3 from this point, 1, 2, 3, and down 4, 1, 2, 3, 4, we would get to this point 5, 1, and that's another point on our line. Now, when it says that it's parallel to 3, -4, if I draw the vector b, and I'll draw the vector b here in orange, if I go over 3 and down 4, I'm going to shoot just a little bit. I would get to that point right there. And if we take this orange one and match it up, notice how perfectly it matches up. That's cheating a little bit, right? It's the idea. But vectors float. So this vector, here is the position vector of 3, -4. But as a direction vector, that 3, -4 can be anywhere. So it can be on there connecting those 2 points. And of course, this orange line would be parallel to the orange line when it was here, because I'm just dragging it and not changing its slope as I go along. So now the vector equation of this line says, and this is what makes vectors so easy to work with. If you had this in y equals mx plus b, you would have to find the slope, right? And the slope of this purple line isn't hard because we already know that the rise over run is -4/3, because we drew those dots. That's easy to find the slope, but if you wanted to write y equals mx plus b, you would still have some work to do to find the b value, right? Or there are other forms of writing, I don't know if you remember, like y minus y1 equals mx minus x1 was another form that you could write the equation and then rearrange. Vector says, let's just make it simple. With the vector equation of a line, all you have to do is have any point to start with. So you could choose 2, 5, you could choose 5, 1, it doesn't matter. Then, once you have your direction vector, just put a t in front of it and say, if you make this orange line bigger, smaller, change its direction, you will always be on the purple line, no matter what. And wherever you end will be a vector that ends on that purple line. It's like, oh, grade 10 math would have been so much easier. Can you imagine? Just, if you find a point and a slope, that's my equation of my line. My equation of my line is y equals point plus slope. Good, done. And no other work to be done. Okay? But from this, if we look at the parametric form, just look at your x coordinates. Your x coordinates are 2 plus 3t. Your y coordinates are 5 minus 4t. And for what we're going to be doing, the least useful one is going to be our Cartesian form. In our Cartesian form, first of all, you're going to solve for t. So I take both of my parametric equations, get t by itself. And then you can equate them. Now, if you wanted to, after you've equated them, you can rearrange this equation, right? I could get rid of the fractions by multiplying by 4 and, oh, sorry, negative 4 and 3. So if I multiply by negative 4, I get negative 4x plus 8. If I multiply by 3, I get 3y minus 15. Heck, I could even get 3y by itself by adding 15 to both sides. And I could solve for y by dividing everything by 3. And I just got the y equals mx plus b form of that line. The y-intercept happened to be 23 over 3. Really useful, really helpful. Can't wait to work with this line with a y-intercept of 23 over 3. But the vector equation says, oh, don't worry about it. Just take any point. It'll make your life easier. Plus, we can do the same idea in 3 dimensions, and it works out perfect. So we realize that maybe this is a better way of thinking about our lines on our graphs rather than our regular y equals mx plus b. If we use vectors instead of actual points that are fixed. Well, we still have fixed points because we still have fixed position vectors. But as long as you have a starting point, you can get to another point easily. So we get another question that you would have had in grade 10, but now in the form of vectors. Here's our one vector. Our vector A is 2, 5. Our direction vector has to be perpendicular to 3, 1. So what do we have to do to make something perpendicular? Well, we can think back to grade 10 math, and if two things are perpendicular in 2 dimensions, then the slopes are negative reciprocals. That's one way to do it, okay? So if I did that method, it wouldn't be hard for me to realize that B has to be the reciprocal, so 1 and 3, and there has to be a negative somewhere in that reciprocal, and it doesn't matter where you put that negative. You could put the negative with the 1 or the negative with the 3. Okay? What are other things that we've recognized? Well, we could use a dot product and say, I need to take 3, 1 and multiply it by something so I get 0. And it doesn't matter what that something is. So for example, if you chose x to be 2, can you see that y would have to be minus 6 for the dot product to be 0? So you could do, or you could pick x is negative 1. Oh, then y would have to be 3. And it doesn't matter what you choose, because your direction vector, as long as it's this or any multiple of that parallel to that, you're fine. So your direction vector could be, I can multiply this by 2, negative 2 and 6. That would be fine. Right? You want to make my life miserable? Choose and multiply them both by 1.732. And I have to do the math and check it. Is this actually right? I shouldn't give you ideas. I know, I just mark it wrong, and then you'd have to prove to me that it's right. And then it'd be more worse, so you can keep it simple. So now we have our point is still 2, 5. our direction vector, -1, 3, and we have our vector equation of a line. Does this one want the parametric and the, parametric. Parametric is just looking at the x coordinate. And the y coordinate. So there's our parametric. Cartesian, you have to solve for t in each of these. So in the one, t would equal 2 minus x. And in the other one, t would equal y minus 5 divided by 3. There's your Cartesian form. And if you wanted to rearrange that and solve for y, you would get y equals mx plus b. We'll do one more in 2 dimensions. And we'll draw a picture to see what's happening here. So if you have the points 1, 4, oh my goodness. Well, this is not efficient. Had to go and choose 8, so it was so much higher. 2, 3, 4, 5, and 0.5, 8. Then there's going to be a purple line that goes through those 2 points. What is the vector equation of that line? Well, we have our blue vector that goes to 1, 4. We have our green vector that goes to 5, 8. Does it make sense that if you wanted to get your direction vector, if you're starting at point A and going to point B, your direction vector is going to be A to B. Now, how do you get from A to B? You get from A to B by going back to the origin and then traveling along position vector B. So this idea of working with our position vectors, -a plus b. In other words, and I'll write b first, 5, 8, because it's easier to subtract. You'd have 5, 8 minus 1, 4. Giving us 4, 4. So our direction vector says, go 4 to the right, go 4 up. That will take you from A to B. Can you see that in, like, if you were thinking slope, if I went over and up, that you're going over 4 and up 4 to go from point 1, 4 to 5, 8. So your slope would be 4 over 4, which could be 1 over 1, which could be just 1. What's our vector equation of a line as a result? Our vector equation of a line is any point. So you could choose to put the 1, 4 here or the 5, 8. It doesn't matter. This can be any vector on the line plus t, and your direction vector, and you could write 4, 4, or 1, 1, or 2, 2, or 3, 3, because they're all the same direction, just parallel to each other. parametric. Your x would be 1 plus 4t. Your y would be 4 plus 4t. So is it wrong if you change this to 1 and 1? Can you see that your parametrics would be 1 plus 1t and y would be equal to 4 plus 1t? It would be a different equation for x's and y's, but they will work out to the same thing. And when you solve for t to get your Cartesian, right, t in the one will be x minus 1 divided by 4. T in the other one would be y minus 4 divided by 4. If they were both 1s on the bottom or both 4s on the bottom, it wouldn't make a difference. And of course, you could simplify that and get y equals mx plus b. But now we can do the same thing if you have 2 points in 3 dimensions. Yeah, I'm feeling like I want to try to draw this. I don't know if this is a good idea. So I'm going to draw my x and my y axes like it's lying on a piece of paper. And then my z axis, ooh, I like the dotted line, yeah, going straight up and down. So 1, 5, 3 would be 1 along your x, 1, 2, 3, 4, 5 along your y, and 1, 2, 3 up. So I would go over to 1, 5, which would be right here, and then this length up 1, 2, 3, 1, 2, 3. This would be my first point. So I went over 1, over 5, got to that point, then I go distance of 3 up. Here is the vector p. The vector q, we need to go 2 over, 4 down. And the nice thing about vector q is it doesn't go up at all. So 2 over 4 down. Here is the vector q. And in 3 dimensions, there is a line going through those 2 points. I'm not sure how helpful that diagram is in the end. It's very hard to visualize things in 3 dimensions on a 2-dimensional piece of paper. But we want to find any point on that purple line. So what do we need? We need a direction vector. And our direction vector will be, I should label q here. Our direction vector is like, well, if you go from P to Q, that's the right direction. Now, how do I get from P to Q? I could use my position vectors. I could go from P back to the origin, and then from the origin to Q. And since our points, I'm going to write Q first, oh no, I read Q wrong. We'll just ignore it. Nobody noticed I read Q wrong? Well, you were just ignoring me. You're like, he's drawing a picture. The picture's going to look terrible anyways, so who cares? You see, I went 4 in the Y, but not 4 in the Z. Actually, wouldn't make too much difference. That's where it should. we can imagine it. So Q is 2, 0, negative 4, minus P, and P is 1, 5, 3. It's not hard to get our direction vector. We get 1, negative 5, negative 7. And now our vector equation of a line, you can choose P or Q. I don't like Q anymore because I made a mistake with it. So I'm going to choose P. And our direction vector, 1, negative 5, negative 7. And we have just found the vector equation of the line through those 2 points. And we can do all the kind of math that we did in 2 dimensions easily in 3 dimensions. Okay? Think of it before today. I tell you in 3 dimensions, you have this coordinate and this coordinate, and you try to draw a picture to see if you could visualize it. And then they go and ask, is negative 1, 3, 5 on that line? And you're like, the best answer before today would be, I don't know. You probably also say, I don't care. That's okay. Okay? But what we can do now is we can say, oh, if it's on the line, and then we look at our parametric equation. So our parametric equation say that x has to equal 1 plus t. Our y and our z coordinate, our y is 5 minus 5t. And our z, let me just double check, is 3 minus 7t. Those are our parametric equations. So if x is negative 1, can you see that this equation says t has to be, x is negative 1, t would have to be negative 2. And if y was equal to 3, that tells me, if I solve for this, that t would have to be 2/5. I can already tell no. Because if it's on the line, there has to be a t that takes me there in that direction. But since I have to go negative 2 for the x and I have to go 2/5 for the y, it's not going to work. Even if this one, here's z, we can, if z is 5, well then t would be, oh, it's bad there too, negative 2/7. So what did we do? We solved for t in each. If t was the same in each, then it would be on the line. But as soon as you have a different t value to get to each one, you're not going in the same direction a certain amount of time. And that's sort of why we use t. T sort of is going to be an application. We're going to use time for this. Okay? We're going to, here's the application, right? You're flying an airplane, and there happens to be a very tall building, and you know where that building is. And so that building is this point right there. You're driving your airplane in a straight line, and you want to know before you get there whether or not you're going to hit that. So in this case, everything works out fine. No, you're not going to hit that. It's going to be all right. What about this point? So again, we will rewrite out our parametric equations, and should just I'm trying to be a shortcut, and my computer's going to freeze on me. Oh, there they are again. So if x is 3, x is equal to 3, can you see solving for t? And sometimes, you know what? Sometimes I like, for showing my work, I like to draw an arrow. I actually plug in 3. This might be nice in your notes, because then you can actually see what you did. Can you see that t would equal 2? And if you plug in -5 for y, -5 equals 5 minus 5t. T is equal to 2. And finally, you plug in 5 for z, 3 minus 7t. Move the 3 over, and you get t is equal to -2/7. No, it's not on the line, and I fooled you all, because this is what teachers always do. They always give you one example that works, and then one example that doesn't work. I bet you were all expecting this one to work before it happened. And it looked like it was going to work, because it was like, oh, it's 2. It's 2 again. Mr. Chair is so predictable. And then I throw a curveball into the question, and once again, no, it's not on the line. You're safe to fly your plane once again. This is the last question that we'll do. That's safe. From now on, danger will abound. So sometimes you will get, and let's add the arrow here, weird combinations of the vector equation line. It's like, oh, let's put together a little bit of the parametric equations and a little bit of the actual equations. Can you see that this is the same as, oh, the point was 3, 5, and then I had t with a 2 and a -5. But they just actually added these vectors together. Because what are you allowed to do? You're allowed to multiply that t inside. So this could be 2t and -5t. And then you can add corresponding elements. Do you remember how to find unit vectors? So it says find the unit vector in the direction of this line. So the direction of this line is, your direction vector was 2 and -5. So we are wanting to find the unit vector in the same direction as B. Can you tell that the length of B, a squared plus b squared, is the square root of 29? That's how long b is. So anytime you want to find a unit vector, you just say, well, I'm just going to make this vector short by dividing it by 1 over the square root of 29, and I have my unit vectors. And finally, it says, find the Cartesian part. So first, to find the Cartesian, we start with the parametric, which is looking at the x value. Then for the Cartesian, you solve for t. So in the first equation, if I got t by itself, it would be x minus 3 over 2. For the second equation, if I got t by itself, would be y minus 5 over -5. and we have the Cartesian. Oh, fire alarm. So R with L is 5, 3, and 0 plus S with -4, 1, and 2. That's a nicer form. And R with M, line M, that one has -3, 7, and 6 plus T and -4, -1, and 0. So we get two sets of vector equations of the lines. We have, and I'll write the parametric ones right beside here, 5 minus 4s, 3 plus s, and z will be 2s. Here, the x is -3 minus 4t. Y is 7 minus t, and z is 6. And we have these two lines supposedly intersect. Now, does it make sense if they intersect, their x coordinates would be the same, their y coordinates would be the same, and their z coordinates would be the same? So we can take our parametric equations and we can create a very big systems of equations. We have 5 minus 4s has to equal -3 minus 4t. From our y coordinates, we would have 3 plus s has to equal 7 minus t. And from our z coordinate, that 2s has to equal 6. I hope you see from the last one, it's not always like this, but the last one's really easy to see that s has to be 3. Normally, if you had s and t in all three of them, you would have to solve a system of equations. Take two of those equations, use substitution, elimination, or matrices, and solve them, and then you would have to check if the third equation still works. Sometimes it doesn't. Sometimes you can have two lines that never intersect. But in this case, s is 3. I could plug it in here, and I would get t is equal to 1, because when s is 3, t is 1. And I could check, does it work for the very first one? When s is 3 and t is 1, yes, it works for all of them. So what's the point that's on both of them? Well, I could use either s or t and plug it into the equation. If I use t as 1, because I can see it here, -3 minus 4, -7. 7 minus 1, 6, and 6 plus 0, 6. So -7, 6, 6 is the point that they have in common. It's important that you have a point in common, because once you have a point in common, you are able to find an angle between them. If they never intersect, there is no angle between them. The number one mistake when this question comes up to find the angle between the two lines is that students don't use the direction vectors, they just use the position vectors. But those position vectors don't show you the angle between. You have to use the direction vectors. The bell's gonna go, we're gonna leave this to solve for tomorrow.